So, good morning. Hi, myself Balasubramanian, from St. Joseph College of Engineering. Today, we are going to have a video lecture on the one-dimensional problem, the displacement and the thermal part. So, coming to the displacement, the problem what we are going to see here is a rod subjected to an axial load P is equal to 600 kilonewton is applied as shown in the figure. Divide the domain into two elements. Determine the following: the displacement at each node, stresses in each element, and reaction at each point node. So here in the drawing, they have given a single bar element where the load is acting at the in between the at the center point of the axial. In the axial direction, the load is acting in the center point direction, and for the displacement, they have given space for 1.2 mm. So we are going to find for this particular load whether the displacement is going to be more than 1.2 or it is going to be less than 1.2. It is a case study example, and it has been asked in many of the Anna University exams. Uh, so here in this problem we are going to divide this element into two elements. They have given divide the domain into two elements. So we are going to divide the domain into two elements. That is, this is going to be first, and this is going to be second. Okay. So the gap for the del L, this is the displacement del L. So we are going to find initially we are going to find whether for the given load condition and for the given length the displacement is going to be more than 1.2 or less than 1.2. For finding that, we are going to go with the strength of materials equation. Del L is equal to load into length divided by area into Young's modulus. So this is the formula. So here they have given the load as 600 kilonewton, that is 600 into 10 power 3 into the length what they have given as 150. That is, from here the displacement is going to happen. So there is not going to be a change in displacement in the second element. The change in displacement is going to happen in the first element only, since it is a cantilever beam. Okay, so we are going to take the length as 150 divided by the area. Area they have given it as 250 mm square, so we are going to directly take 250, and the Young's modulus is also given 2 into 10 to the power of 5 Newton per mm square. So by calculating this, you will be getting an answer as 1.8 mm, which is greater than the space 1.2 mm. So here we are going to consider the node number. Okay, here going to consider the node number. For the element 1, it is going to be 1, 2, and 3. So you will be having a displacement u1, u2, and u3. So the displacement for u3. So apart from this given, the displacement another given is nothing but your u3 is given as 1.2 mm. Since the actual displacement is 1.8 mm, so the space between the component and the wall is 1.2 mm, so we can take only u3 as 1.2 mm. So what are they given? They are given the load, they are given the length, they have for two element, they have given the area, they have given the Young's modulus. So if you want to take the Poisson's ratio, you can take the Poisson's ratio, but we are going to take only Young's modulus for your stress strain relationship matrix, so there is no need for any Poisson's ratio. So we need to find the stress in each element. Stress formula sigma is equal to E into du by dx. So strain into E into du by dx. So at reaction is nothing but R is equal to F minus U. R is equal to F minus U. This will be the formula we are going to follow. So coming to the elemental equation. So we will go with elemental equation. So this is a separate one for finding the displacement. So elemental equation, we know for element 1, for element 1 and 2, the both it is going to be the same. For element 1 and 2 it is going to be the same. So we will be having force 1 and force 2. So F1 and F2 is equal to A E by L, that is A1 E1 by L1 into 1 minus 1 minus 1. 1 is going to be nothing but is going to be 1 area is nothing but 250. Here we will solve 250 into is 2 into 10 to the 2 into 10 to the power of 5 divided by L1 is nothing but 150, which comes around 3.33. That is 3.33 into 10 to the power of 5, 1 minus 1 minus 1, 1. Okay, so we will consider 1 into 10 to the power of 5 outside, and 1 minus 1 minus 1, 1 will be the solution. So this is going to be for the node 1, node 2, node 1, node 2. Similarly, for element 2, we will be getting the same solution. For element 2, we will be getting the same solution. That is K1, this is K2. K2 is equal to 1 into 10 to the power of 5, 3.33, 3.33, and minus 3.33, 3.33. So by joining K1 and plus K2, that is nothing but this is going to be your second and third. This will be your second and third. So we will do 1, 2, 3, element 1 and element 2. Okay. So K1 plus K2. So we are going to make a global matrix. Global K matrix. So the global K matrix is going to be, we will be having a common 1 into 10 to the power of 5 for both the term. So 3.33 minus 3.33 minus 3.33, 3.33 plus 3.33. So whole together it is going to be is nothing but, right in the bottom, is nothing but 6.66. 6.66 minus 3.33, here minus 3.33 and plus 3.33. So we are not having the value for A31, that is going to be 0, and A13, that is also going to be 0. This is the K global matrix. So we know the equation for force. So here it is going to be for K2, instead of K2 we can consider it as force. We will be having F2 and F3. Okay, so considering the global stiffness matrix, we know F is equal to K into U. So the displacement here will be U2, U3. There you will be getting the displacement as U1 and U2. So global stiffness matrix. So force. So we are going to consider the force. So by considering the force, there is no force at node 1, there is no force at node 3, we are having the force only at the node 2. So the force will be 0. Next will be 6 into 10 to the power of 3, that is 6 kilonewton. So we will be considering as 6 into 10 to the power of 5. Okay, 6 into 10 to the power of 600 kilonewton. So we are considering as 6 into 10 to the power of 5, and 0 is equal to the global stiffness matrix, that is 1 into 10 to the power of 5, 3.33 minus 3.33 0, minus 3.33, 6.66, minus 3.33, 0, minus 3.33, 3.33 for the displacement u1, u2 and u3. So u1, u2, u3 we know the value, it is 1.2. We derived and we found that this space with beyond the space only the displacement is going, so the 1.2 can be taken. So this is the solution. So we need to apply the boundary conditions. Okay, by applying the boundary condition, what is the boundary condition here? Here in the node 1 there is no displacement, right? Here in the node 1 there is no displacement, so we will be considering u1 as 0. So when you are going to consider this u1 as 0, we are going to consider this u1 as 0, the first row and the first column, the first row will be eliminated. This is going to be 0 throughout. So the final equation will be 6 into 10 to the power of 5, 0 is equal to 6.66 minus 3.33 into u2 and minus 3.33 into 3.33 into 1.2. So by solving this equation, you will be finding the u2. So 6 into 10 to the power of 5 is equal to 6 into 10 to the power of 5 is equal to 6.66 u2 minus 3.33 into 1.2, which will be having, you will be getting u2 as 1.50 mm. 1.50 mm. So we have found the displacement u2 as 1.50 mm. Okay. Next we will be finding the elemental stress. So before going to the elemental stress, we need to know the equation for elemental stress. For element 1, we will be having, so we have already discussed the equation. So sigma is equal to E into du by dx. Sigma is equal to E into du by dx. So this du by dx will be E into u2 minus u1 by L1 for element 1, and for element 2, it is going to be E into u3 minus u2 divided by L2. So we are going to substitute. So for element 1, it is going to be, um, sigma 1 is equal to E into u2 minus u1 divided by L1. That is nothing but we know the value of u2, we know the value of u1. u2 it is 1.5 minus 0 divided by 150. E is going to be 2 into 10 to the power of 5. That is nothing but 2000 Newton per mm square for element 1, and for element 2. So for element 2, it is going to be sigma 2 is equal to E into u3 minus u2 divided by 150. For E it is going to be 2 into 10 to the power of 5. So you will be getting the term 1.2 minus 1.5. So you will be getting the term of negative, that is 400 Newton per mm square, which here the positive is considered its as tensile force and for stress, and the negative it is nothing but the compressive stress. Okay, so we have found the out of 2 we have found the displacement and the elemental stress. Next, coming to the reaction force. So coming to the reaction force R, that is nothing but reaction force R is nothing but K into U star minus F. So this U star is not required. So K into U minus F. So this is the equation for the reaction force. This is the equation for reaction force. So we know the value of K. Okay, we know the value of K. K is nothing but 1 into 10 to the power of 5, 3.33 minus 3.330 minus 3.33, 6.66 minus 3.330 minus 3.33, 3.33 into U1, U2, U3. So U1 is 0, U2 is 1.5 and U3 is 1.2 minus F1, F2. So we know the value of F1, F2, F3. So F1 will be 0, F2 is 6 into 10 to the power of 5 and F3 is also 0. So this is the equation for finding. So when we are going to find, it is going to be by solving. So here it is going to be 3 cross 3, 3 cross 3. Here it is going to be 3 cross 1. Okay, so you will be getting the final answer as 3 cross 1. So when you are going to multiply by 1 into 10 to the power of 5. Okay, when you are going to multiply by 1 into 10 to the power of 5. So we need to multiply. So you will be getting the final term. You will be getting the final term as minus 5 into 10 to the power of 5, 6 into 10 to the power of 5 and minus 1 into 10 to the power of 5 minus 0, 6 into 10 to the power of 5 and 0. So this will be the answer. So when you are going to consider the reaction, so you will be getting, so by minus, you will be getting the answer as minus 5 into 10 to the power of 5, 0 and minus 1 into 10 to the power of 5. So here you will be getting the reaction 1, R1 as minus 5 into 10 to the power of 5, R2 reaction at point 2 is 0 and reaction at point 3 is minus 1 into 10 to the power of 5. Okay, that is nothing but this negative denotes that it is by summing up the reaction force, that is R1 plus R2 plus R3, you will be getting minus 6 into 10 to the power of 5. That is nothing but the applied force. It is nothing but the applied force 6 into 600 kilonewton. So finally the result is being arrived. So the result is being written as, for first they have asked the displacement. So displacement, so U1 will be 0, U2 will be 1.5 mm, U3 will be 1.2 mm. So second is your elemental stress. Elemental stress sigma 1 is equal to 2000 Newton per mm square and sigma 2 is minus 400 Newton per mm square. Next is your reaction force. Reaction force is nothing but R1. R1 is equal to minus 5 into 10 to the power of 5 Newton per Newton, and R2 is equal to 0. R3 is equal to minus 1 into 10 to the power of 5 Newton. So this is the solution for this particular problem. Next we will go with the structural problem. Okay. So in this problem, we are going to see loading is going to be acting uh, on the second node as similar as the previous problem. There we took the area in a similar manner since it is going to be the single rod and the load is only acting in the center position. Here we will be having two different material, that is one is your aluminum and another one is your steel, and the load acts on the joint share of the aluminum and the steel. Here we are going to calculate the assembling of the K and F matrix. Second is the nodal displacement. Next is stresses in each material and reaction at each nodal point. So here the nodal displacement is nothing but U1, U2, U3. The assemblage of K and F matrix is based on the nodal displacement only, and the stresses in each material and the reaction. Here you will be having the displacement at U1 is equal to 0 and U3 is equal to 0 since based on the boundary conditions, and you need to find only the U2 portion. Okay, so coming to the equation. So here for aluminum they have given us A1, E1 and alpha 1, A2, E2 and alpha 2. So here we are going to find the elemental stress. So first we are going to find the K matrix. So for finding the K matrix, we know the formula K is equal to AE L 1 minus 1 minus 1 1. So for element 1, in the single slide itself we will make it for element 1. Element 1 you will be having area as 1000 into E1 is going to be 7 into 10 to the power of 4. They have given us 0.7 into 10 to the power of 5. We are giving us 7 into 10 to the power of 4 divided by 200. The length 200, 1 minus 1 minus 1 1, which is going to be 1 into 10 to the power of 5. 1 into 10 to the power of 5 into 3.5 minus 3.5 minus 3.5, 3.3 for element 1. It is going to be K1 for the node 1, 2, 1, 2. And for element 2, for element 2, it is going to be 1500 into 2 into 10 to the power of 5 divided by 300, the length is 300 as mentioned here, into 1 minus 1 minus 1 1. It is going to be, I think it's going to be 1 into 10 to the power of 5, 10 minus 10 minus 10, 10. That is going to be for the node 2, 3, 2, 3. Okay. So 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 we have found the elemental stiffness matrix. So elemental stiffness. So we need to for next we need to find the global stiffness matrix. Global stiffness matrix is nothing but uh, K is equal to K1 plus K2. K1 plus K2. So K1 plus K2 is nothing but you will be putting the matrix as 3.5 minus 3.5 minus 3.5, 3.5 plus 10 minus 10 minus 10 plus 10, and you will be putting 0. So this is for the nodes 1, 2 and 3, 1, 2 and 3. So we know the equation for force F1, F2 and F3 is equal to the K, that is 1 into 10 to the power of 5, 1 into 10 to the power of 5. So 1 into 10 to the power of 5, 3.5 minus 3.5, 0, 3.5 minus 3.5, 13.5 minus 10, 0 minus 10 and plus 10. So we need to find the force. Next we need to find the force vector. So force vector. So the force vector for element 1. For element 1 is going to be F1, F2 is going to be E1 A1 alpha 1 del T minus 1 plus 1. So we know the E1, A1 and alpha 1 has been given, and also the del T has been given. So we know 0.7 into 10 to the power of 5 into area is going to be 1000 into 23 into 10 power 6 is your alpha 1, that is your temperature coefficient, and into 30 for the term minus 1, 1. That is nothing but 1 into 10 to the power of 5 minus 0.483 and 0.483. Okay, this is for your element 1. This is for your element 1. Coming to the element 2, force vector for element 2. Force vector for element 2. Same, it is going to be F2, F3 is equal to E2, E2, A2, alpha 2, del T minus 1, 1. That's nothing but E2 is 2 into 10 to the power of 5. Alpha 2 is going to be 1000. A2 is equal to 1500. Alpha 2 is nothing but 12 into 10 to the power of minus 6 into 30. So del T is going to be the same. The temperature coefficient is going to be the same. So by following it, you will be getting the answer as 1 into 10 to the power of 5 minus 1.08, 1.08. So by the global force vector, the global force vector is equal to F1, that is 1 into 10 to the power of 5. We are going to take it as common. We know the initial value is 0.483, 0.483 minus 1.08 and 1.08. So you will be getting the value as minus 0.483 minus 0.597 and 1.08 will be the force vector, that is global force vector F1, F2 and F3. Okay, so here next we are going to substitute the value for in the term F is equal to K into U. Okay, so F is nothing but 1 into 10 to the power of 5, or we will write it as minus 0.483 into 10 to the power of 5 minus 0.597 into 10 to the power of 5 and 1.08 into 10 to the power of 5. For the k value, 1 into 10 to the power of 5 being common, we'll consider it as 3.5 minus 3.50 minus 3.5, 13.5 minus 10, 0 minus 10 and plus 10 for the displacement u1, u2 and u3, u1, u2 and u3. Okay, so u1, u2 and u3 we are applying, and here we are going to add the center node will be having the force of 4 into 10 to the power of 5. Okay, 4 into 10 to the power of 5. So that is going to be equal to, so when you are going to add, it is going to be, so this term is going to be 3.403 into 10 to the power of 5. So this is going to be the solution. So here we are going to apply the boundary condition. So what is the boundary condition? As said before, we'll be having a boundary condition. So here it will be 0, u1 will be 0 and u3 will be 0 since it is insulated or it is in the wall. So there will not be any displacement towards one direction. So u1 and u3 will be 0. So boundary condition u1 is equal to u3 is equal to 0. So since u1 and u3 is 0, we are considering the first row and the first column to be 0 and the third row and the third column to be 0. So you will be writing the equation as 3.403 into 10 to the power of 5 is equal to 13.5 u2. 13.5 into 10 to the power of 5. 13.5 into 10 to the power of 5 u2. So you will be finding the u2 as 0.2521 mm. So this will be the displacement function. Okay, this will be the displacement function. So next coming to the elemental stress. So elemental stress, as said before, elemental stress, it is going to be E sigma is equal to E into du by dx minus, since you have a temperature, E alpha del T will be added to the existing structural equation. So we know the du by dx, E into du by dt is u2 minus u1 by L1 minus E1 alpha 1 del T. So by solving 2 into 10 to the power of 5. Okay, it is going to be point for the element 1. For element 1 it is going to be 0.7. 0.7 into 10 to the power of 5 into u2 is going to be 0.2521 minus 0 divided by the L1 is going to be 200 minus same E1 alpha 1 is going to be 0.7 into 10 to the power of 5 into alpha 1 is going to be 23 into 10 to the power of 6 minus 6 into 30. So by solving it, you will be getting sigma 1 as 39.935 Newton per mm square. So this is considered as tensile stress, since there is no negative for element 1. So similarly for element 2, sigma 2 is equal to E2 u3 minus u2 by L2 minus E2 alpha 2 del T. So E2 is 2 into 10 to the power of 5, u3 is 0 minus 0.2521 divided by L2 will be 300 minus E2 is nothing but 2 into 10 to the power of 5 into 12 into 10 to the power of minus 6 into 30. So you will be getting the solution as sigma 2 is equal to minus 240.66 Newton per mm square. That is nothing but the compressor stress. Okay. So coming to the reaction force. The reaction force equation is nothing but R is equal to K into U minus f. K into u minus f. We know the value of k. K is nothing but 1 into 10 to the power of 5 minus 3.5, sorry, plus 3.5 minus 3.50 minus 3.5 plus 13.5 plus 13.5 minus 10, 0 minus 10 plus 10 into u1, u2, u3. We know the u1 value is 0, u2 value is 0.2521, u3 is 0, and force it is going to be minus 0.483, 3.403, and 1.08. So here also you will be having 1 into 10 to the power of 5. So when you are going to multiply, you will be getting the term as by multiplying this is 3 cross 3 and this is 3 cross 1, you will be getting the final answer as 3 cross 1, and this is also 3 cross 1. So you will be getting the answer as 1 into 10 to the power of 5 minus 0.8823, 3.403 minus 2.521 minus 1 into 10 to the power of 5 minus 0.483, 3.403 and 1.08. So the final answer, that is the R1, R2, R3 is given as R1, R2, R3 is given as 1 into 10 to the power of 5 minus 3.993, 0 minus 3.601. Okay, so we need to check whether it is in equilibrium or not. So we are going to consider R1 plus R2 plus R3 is equal to the force applied, that is 4 into 10 to the power of 5, right? So 4 into 10 to the power of 5. So we know the R1 value as minus 0.3993 into 10 to the power of 5 plus R2 is going to be 0 and R3 is going to be minus 3.601 into 10 to the power of 5 Newton is equal to 4 into 10 to the power of 5. Okay, 4 into 10 to the power of 5. So by summing it up, we'll be getting minus 4 into 10 to the power of 5 is equal to 4 into 10 to the power of 5. It is LHS is equal to RHS. So the solution is correct. So the final answer. So coming to the final answer. So final results. So we'll go with the results. So they are asked K matrix. K matrix, it is nothing but 1 into 10, 1 into 10 to the power of 5, 3.5 minus 3.50 minus 3.5, 13.5 minus 10, 0 minus 10 plus 10. This will be the K matrix. The F matrix is going to be 1 into 10 to the power of 5 and 0.483, 3.403, 1.08. Okay, next will be your displacements. So this is the first. Second is your displacement u1 0, u2 0.2521 mm and u3 will be 0. Next is your elemental stress. Elemental stress is nothing but sigma 1 is equal to 39.935 Newton per mm square. This is tensile, and sigma 2 is equal to minus 240.066 Newton per mm square. It is nothing but compressor. And the fourth is your reaction force. R1 is equal to 0.3993 into 10 to the power of 5 Newton. Next is your R2 is equal to 0, and R3 is equal to minus 3.601 into 10 to the power of 5 Newton. So this is the final results we have arrived, and this is how the problem has been solved. So there is not a much difference between the structural and the temperature. In the structural, we will be considering directly the force. If there is no force, we will consider it as zero. But in temperature, there is an external temperature array, so we will be considering the temperature effect, that is EA alpha del T, to the equation for the force. So this is how the problem has been solved. This is the difference between the structural and the thermal analysis. Thank you.